Hello, I'm going to give a lecture on steps, stairs and ramps today. This is an important element of almost every building design that you will ever have to undertake. It requires a certain level of technical knowledge, and I hope this very brief lecture will give you that introduction to the elements that you need to consider when you're putting together a staircase. On the ground floor, it's very clear most buildings, when they occupy a piece of land, have to follow the topography of the land. In this first slide, we've got a Cistercian monastery at La Tournai in the south of France. The monastery is built on the hillside. The church itself, which you can see at the top of the staircase through an open door, a little tiny window, is on the highest point of the site. And the other elements of the monastery, this photograph taken in the cloister, follows the slope of the ground. And therefore, steps are introduced to take you from one part of the site inside, outside the building to another. It's just a feature of how buildings sit on their sites. In a town, also in France, Auch, the arrangement of the town, the main square being at the very, very top of a hill, the routes up to the main square from the lower surroundings, generally by staircase. The roads in the town itself follow the contours. There are a series of concentric ring roads, if you like, around the central square, which contains the cathedral, town hall, all the public buildings. A very remarkable town which makes the most of using staircases to get from one part to another. In the small alleyways in Auch, the handrails which help the inhabitants to pass between one street and another are a feature. And it's a very lovely thing that the designers of these stairs and these handrails have taken quite a lot of care in making them both very simple and very elegant. The choice of materials, the way that they are started and finished gives the whole feel to the city quite a nice completeness. Other examples of staircases and access, in this case, the Jantar Mantar, which is an astrological observatory built in the close to the centre of Delhi, is a series of structures accessed for taking measurements of the sun and the moon and the stars, very precise geometries to the surfaces that record the shadows and the alignments that are taken by the astrologers in the various buildings on the site. Again, in Delhi, there are many wells. These are called step wells, which fill and reduce during the seasons with water. Access to the water being via these very dramatic staircases, which go down from the street level down to the water table, which of course varies as the rain comes and goes each season. Staying in India and looking at a more modern example of the use of ramps, this Sorry about that. This is a photograph of the High Court building in Chandigarh. You can see the ramps here that allow the judges and the various representatives of the cases to proceed, perhaps avoiding one another outside the courtrooms. The length and the amount of space taken up by these ramps, you can see, is very considerable. Staircases, on the other hand, can be very compact. There are much fewer restrictions, I feel, on the use of stairs than there are on ramps. But nevertheless, safety, lighting, those sorts of issues, they always occur whenever you consider the design of a staircase. Externally, this is an example of the access to the entrance from a lower level of the Nottingham Contemporary Art Centre. It clearly, I hope, illustrates this notion of breaking a very long staircase into a series of shorter stairs with landings, both to break up the monotony of the journey up to the top of the staircase, but also to give people space to take a breath on the way up. The geometry of staircases isn't infinite. There's only a finite number of options. And in this diagram, you can see, starting at the top left with the straight flight staircase, the introduction of winders. These are the angled steps, which are narrower at one end, wider at the other, which gradually, as you add more and more of those into the arrangement of the staircases, naturally turns into a spiral staircase, which is shown at the top right. That's a natural, as it were, progression at the top there. In the middle line, we've got the feature of introducing landings, which break up the staircase, limit the number of steps in a flight. Each section of the staircase is called a flight. The UK building regulations stipulate that you're not allowed to have more than 16 risers, so that's 15 treads between landings. In the centre of that middle row of diagrams, you can see what's called the classic dogleg staircase. That's a staircase that goes up in one direction, there's a landing, and then returns back in the opposite direction. That's the most compact staircase, generally used when you want to be able to return to the place in the plan at the next level where you set off. So it's quite a useful mechanism for orientating yourself on each floor of a multi-storey building. Middle row right hand side, you can see there a very grand staircase which splits. It's very inefficient in the way it's organised, but also very grand and provides a wonderful moment when you might enter from on high in your evening clothes to impress the audience who are waiting for you below. On the bottom row of diagrams, you've got the practicalities of staircases, moving somebody on a stretcher up and down a building, or in even the worst case, in their coffin, is a practical issue, and one might have to consider it in certain buildings that you might be having to consider. There are some restrictions on the dimension that you can apply to a staircase. So in table 1.1, rise and going, this is taken from part M of the building regulations and is the most important set of numbers that you need to consider when you're considering your design of the staircase. There is an increased requirement for the staircase to be a gentle, easygoing staircase as it becomes more and more public. You can see in the bottom text block where the asterisk shows what rise and going actually means, that the rise, that is the vertical height of each step, times 2, plus the going, which is the horizontal part of the step. 2 rises and 1 going must come to between 550 and 700 millimeters. That's a requirement to get the staircase to work out, to conform to the building regulations. And at the end of this talk, we'll be asking you to go and measure your own staircase and check what 2R plus G is, and hopefully we can compare at some time in the future different results, and you will be able to see how there's a limit on the steepness or the lack of steepness of various staircases, and what the feel of that gives you as you move up and down the staircase. There is a requirement for a clear space above each staircase, minimum headroom, as described here in diagram 1.3. It's a dimension which is derived from the line of the pitch of the staircase, the pitch line being the line that connects all the noses, that's the junction of a rise and a going, all the nosings of the staircase, generating that dotted line that you can see there, which is called the pitch line. And you have to maintain above that a clear distance of 2 meters to the next obstruction or the next ceiling or the next sloping soffit of perhaps a staircase above. That's an absolute requirement, and you need to check by drawing a section through your staircase that that all works for you. In order to allow people to come up and start up a staircase and leave a staircase, especially if they're infirm and they need to hold onto a handrail, there are requirements for handrails which need to extend at 300 millimeters beyond the bottom step and the top step, and this is described in diagram 1.11. It's quite important that these are maintained. It means that people can steady themselves before they go down or embark on going up the staircase. It's quite a useful little check. So it does mean that you cannot put, say, for example, a door on that wall where it might conflict with that projecting handrail. In diagram 2.1, there are a set of rules about the steepness of ramps, the length of each section of the ramp, and where landings are required. The steeper the ramp, the more landings required, and that is a sort of law of diminishing returns as well, because effectively the ramps with their landings get longer and longer and longer, even though they are steeper. It's worth just checking out, maybe by sketching out a few diagrams, how that all works, and you'll get a sense of it and how much space a ramp might take up. So, for example, a typical floor-to-floor height, say of 3 meters, requires a minimum length of ramp of 36 meters at 1 in 12. So that's 36 meters. That's a long, long way. Barriers at the edge of staircases, at terraces, at balconies, they are generally, in a domestic residential situation, 900 millimeters high, but in public buildings, balconies, terraces, that sort of edge where there's a risk of falling, they have to be a minimum of 1100 millimeters. Those are the two vertical dimensions for barriers that you need to keep with you as you consider what might be required on a terrace or a rooftop or a roof edge, something like that. There are little cheats. The rise and the going can be fiddled with a little bit by overlapping the tread of the step above with the step below. However, still the geometry of the staircase, the going and the rise, as you can see here in both of these two versions where the treads are offset, the going and the rise is determined by the vertical and horizontal dimension between the nosings of the staircase, the nosings being the junction between the rise and the tread. There's also a question of what happens underneath the staircase, the soffit of a staircase. How does that look when the two flights of a staircase might meet? How does that resolve itself on the ceiling? And it's a useful little check here of how the various configurations of steps work out where they meet on the soffit underneath. And you might want to think about that if you're trying to get everything to line up with your soffits and your staircases. It's not entirely straightforward and does, to a greater or lesser degree, as you can see here on these staircases, depend on the thickness of the staircase structure. Some can be relatively slender, others are required just through pure geometry to be much thicker. Finally, a couple of examples of unusual staircases. This one, a 19th century staircase in a villa in Portugal, where the steps are cantilevered out from the wall. You can see top left, the soffit of this staircase is a series of inclined, interlocking surfaces which are the underside of these triangular shaped treads. Each one is built into the wall. The end of each tread is a rectangular block. The tread itself is a triangular shape, the horizontal top surface being the actual surface that you walk on. But underneath there, each one sits on the one below and is like a series, a progression of blocks going off in a sort of diagonal arrangement up the wall. The blocks are built into the wall, and therefore the weight of the wall above the staircase stops those blocks rotating. The blocks sit, or the treads I should say, sit on each other. So once the blocks built into the wall cannot rotate, the staircase holds itself up. This is a particularly fine example. It's quite wide. It's about 1.5 meters wide. Very grand, very remarkable structure. A more modest example here in the Fatehpur Sikri, a little city, new city, built as the potential capital of India outside Agra, though never actually quite occupied, shows a very simple form of stone construction, the treads, the risers being built into that wall, then cantilevering out each step, each riser resting on the one below until you get to the landing at the top, which is borne by those two corbels. You can see them at right angles to the wall, the corbels holding the landing that the staircase comes up onto, and then the access to the staircase is through that gate at the top. I would urge you all to go measure a staircase near you, record the rise and the going, calculate the pitch line of the staircase, how steep it is. I think the maximum pitch that one can have in a domestic stair, a residential stair, is 42 degrees. So you cannot get up to 45 degrees. Even this one in India that you can see here in front of us, that's probably about 40 degrees. It's quite a nice, generous staircase, not too steep, not too flat, quite a good copy to think about. And you should do that calculation of 2R plus G. That should come to between 550 and 700, and just check how it works for your particular staircase. That's it. Thank you very much. Bye-bye.